Water treatment systems form a foundational part of urban and regional infrastructure. They are designed to provide reliable supplies of treated water and to manage used water on a continuous basis. The systems operate around the clock. Their functioning is integrated with other infrastructure systems, including distribution networks, storage reservoirs, and transportation of inputs such as chemicals and energy. In large service areas, treatment plants and related facilities are arranged to serve neighborhoods, industrial zones, and public services without interruption. The primary function of potable water treatment is to transform raw source water into water that meets regulatory and technical quality standards. Source water arrives from surface sources, such as rivers and lakes, or from groundwater. In all cases, that incoming water is subject to variable conditions. Weather changes, seasonal shifts, and human activity affect quantity and quality. Treatment facilities are designed to accommodate those variations. They adjust processes continually to maintain consistent output quality. Treatment processes are arranged in sequences. Initial steps remove large debris and suspended materials. Subsequent steps focus on separating fine particles, reducing organic matter, and controlling biological organisms. Disinfection is applied to reduce the risk of disease-causing microorganisms. Each step contributes to a defined set of targets, such as clarity, taste and odor, and limits on chemical contaminants. Operational control ensures that those targets are met for every volume of treated water that leaves the plant. Wastewater treatment serves a different but complementary purpose. It collects used water and conveys it to treatment facilities for removal of solids, organic load, and nutrients. The treated effluent is returned to receiving waters or, in some cases, prepared for reuse. Wastewater systems operate continuously to handle flows from households, industry, and stormwater. Processes within these systems include physical removal of solids, biological treatment to break down organic matter, and chemical or physical polishing steps to reduce remaining contaminants. Monitoring ensures that effluent meets regulatory requirements intended to protect downstream uses and ecosystems. Both potable and wastewater systems are sized and arranged with redundancy in mind. Redundancy is achieved through parallel treatment trains, standby equipment, and multiple intake or discharge points. Redundancy supports continuous operation during maintenance, repairs, or fluctuations in demand. Backup power supplies are typically provided. Spare parts and alternate chemical supplies are maintained to reduce the likelihood of interruptions. The design reflects expected peak demands as well as routine daily variations. Demand on water systems follows predictable patterns. Daily cycles show higher consumption in morning and evening, hours and lower flows at night. Seasonal patterns also influence demand. Treatment operations adapt to these cycles by adjusting pumping rates, flow distribution, and process intensity. Storage reservoirs and elevated tanks are used to smooth short-term variations and to provide emergency reserves. Distribution systems are managed to balance pressure and to deliver treated water to distant service areas. Pressure management also supports non-domestic needs, such as fire suppression and industrial processes. Continuous monitoring is a central feature of modern water treatment operations. Sensors track flow rates, turbidity, chlorine residuals, pH, and other parameters. Data from sensors feed control systems that adjust chemical dosing, filtration rates, and pump operation. Supervisory control and data acquisition systems, commonly known as SCADA, enable operators to observe conditions from a central control room or remotely. Routine laboratory testing supplements sensor data. Laboratory analyses confirm the presence or absence of specific contaminants and provide a basis for regulatory reporting. Maintenance is scheduled and performed regularly to preserve reliability. Routine tasks include cleaning filters, inspecting pumps, calibrating sensors, and replacing worn mechanical parts. Preventive maintenance helps prevent sudden failures. Planned outages are coordinated with redundancy measures so that treatment continues on alternate lines. Asset management systems record maintenance activities and inform decisions about capital upgrades. Long-term planning addresses equipment life cycles, anticipated population growth, and changes in regulatory requirements. Operations are governed by regulatory frameworks that specify water quality and discharge criteria. Compliance requires both routine monitoring and formal reporting. Permits define allowable limits for contaminants and set conditions for intake and discharge. Operators follow procedures that are documented and auditable. When abnormalities are detected, protocols specify corrective actions and notification requirements. Regulatory oversight provides an external check on performance and helps align treatment practices with public and environmental health objectives. Interconnections between systems provide regional resilience. Multiple utilities sometimes share resources, such as emergency pumping or treatment capacity. Water transfers and interconnections can redistribute supply during periods of shortage. Coordination among utilities, watershed managers, and emergency services supports responses to extreme conditions. Planning at the regional level considers source protection, distribution interties, and potential demand shifts caused by economic or demographic changes. Energy use is a significant consideration in continuous operation. Pumps, aeration systems, and chemical feed systems consume power. Energy supply reliability affects operational planning. Many facilities include measures to manage energy use, such as variable speed drives, optimized pumping schedules, and, in some cases, on-site energy generation. Energy planning is part of operational planning because consistent electricity supports steady treatment performance. Human resources play an essential role. Trained operators monitor systems, perform manual adjustments, and interpret data. Technical staff perform maintenance and laboratory analysis. Administrative personnel manage procurement, regulatory reporting, and asset planning. Staffing structures are designed to provide coverage for 24-hour operation with shift schedules, on-call arrangements, and training programs to ensure continuity of knowledge and capability. Treatment systems also support economic activity. Reliable water supply enables commercial and industrial processes. Effective wastewater management protects downstream water bodies that serve other uses. In this way, continuous operation of treatment systems contributes to broader municipal and regional functions. That role is practical and technical. It is achieved through infrastructure, processes, personnel, and procedures that operate together on a continual basis. When new demands arise, systems are adapted through upgrades, capacity expansions, or operational changes. Retrofit projects may add treatment steps, reconfigure distribution, or improve energy efficiency. Planning processes evaluate existing capacity, forecast future needs, and prioritize investments. Investments are implemented through staged projects that aim to maintain continuous service while construction is underway. The continuous operation of water treatment systems is thus a combination of technical processes, monitoring, maintenance, and planning. Each element supports the steady production of treated water and the effective management of used water. The systems work within interconnected networks to serve broad geographic areas. Their steady function depends on equipment, human oversight, regulatory compliance, and coordinated regional planning. Raw water begins its path to treatment at intake points, located where a source can be accessed reliably. Sources commonly include rivers, lakes, reservoirs, groundwater wells, and coastal waters. Each source presents different physical conditions. Intake design adapts to those conditions. The primary goal of an intake is to move water from the source into the treatment facility in a controlled and measured way. Intake structures are built to manage flow and to prevent large debris from entering the treatment process. Simple intakes may be pipes or conduits placed below the water surface. More complex intakes include intake towers or intake bays that allow operators to select water from different depths or positions. Selection of intake depth can affect temperature and particulate levels. The ability to select depth helps manage variations in the source throughout a season. Flow control is a fundamental function at the intake. Gates, valves, and weirs regulate the volume of water entering the facility. Gravity can supply flow where elevation differences exist. In many cases, pumps provide the necessary lift and pressure. Pumps are sized for expected maximum demands and often include spare units to provide redundancy. Flow meters measure the rate of water entering the system. These measurements feed into operational controls and recorders. They also provide data for process adjustments further downstream. Screens and racks are the first physical barriers within an intake. Coarse screens intercept branches, leaves, and larger floating objects. These screens are sometimes equipped with mechanical rakes that remove the accumulated debris. Finer screens follow to capture smaller solids. Screen openings vary, but the principle is consistent. Reduce solid load before water reaches treatment basins. Screen cleaning can be automatic or manual. Regular cleaning maintains throughput and prevents excessive head loss across the screen. A forebay or settling forebay often follows the initial screens. A forebay is a basin where flow slows and heavy particles settle out. Slowing the flow reduces the transport of sand and larger sediment. Forebays help protect pumps and downstream equipment from abrasive wear. They also provide a location for sampling raw water. Water quality samples taken at the forebay give an early indication of turbidity, color, and other parameters. Data from these samples inform treatment steps that follow. Intake placement considers sediment transport and local hydraulics. Water intake openings are commonly placed away from areas of high sediment deposition. They may be positioned adjacent to deeper water or within engineered channels. In some designs, intake structures include diversion channels that steer floating debris away from the intake path. Placement also considers seasonal changes in water level. Intake openings can be adjustable or have multiple ports to accommodate these changes. Groundwater intakes differ in approach. Wells draw water through screened casings that filter out coarse sand and gravel from the aquifer. Well design focuses on achieving a steady yield while minimizing the entry of fine particles. Well pumps raise the water to the surface and into the treatment facility. Infiltration galleries and collector wells are alternative groundwater collection methods. They use subsurface conduits or perforated pipes to gather water over a larger area before transfer to the plant. Coastal or estuarine intakes require consideration of salinity and marine organisms. Intake locations may be set to avoid strong tidal inflows that increase turbidity. Screens for marine intakes often include measures to reduce entrainment of small organisms. Some facilities use intake tunnels that extend offshore to draw water from more stable layers. In such cases, intake design and location aim to minimize the amount of suspended material entering the system. Stormwater and surface runoff can be an interim source for auxiliary systems. When used, these sources typically pass through preliminary settling or detention basins before entering a treatment plant. These basins reduce peak flows and allow heavier sediments to settle. They also provide a buffer against sudden spikes in turbidity following rainfall events. Control systems monitor intake conditions continuously. Sensors measure water level, flow rate, turbidity, and sometimes basic chemical indicators. Alarm thresholds alert operators to conditions that require attention, such as sudden increases in turbidity or reductions in flow. Automated controls can adjust gate positions or pump speeds in response to sensor inputs. Manual interventions remain part of regular operation, especially during maintenance or unusual events. Maintenance at intakes addresses fouling and wear. Screens and rakes require cleaning and occasional repair. Intake gates and valves need lubrication and inspection. Pumps are inspected for seal integrity and wear. Dredging may be necessary where sediment accumulation impedes flow. Ice formation in cold climates requires special design features, such as heated intakes or intake heaters, to maintain function when temperatures drop. Environmental regulatory requirements influence intake design and operation. Permits may specify intake velocity limits to reduce the movement of aquatic organisms toward the intake. Fish protection devices such as fine mesh or behavioral deterrents can be required where regulated species are present. Monitoring and reporting of intake performance are often part of permit obligations. These regulatory measures focus on measurable limits and operational practices rather than qualitative judgments. Redundancy and reliability are central to intake design. Many facilities include multiple intake lines or parallel pumps. Backup power systems, such as generators, provide continued operation during power outages. Redundant components reduce the likelihood of interruptions to water supply. Operational plans outline procedures for switching between intake lines or isolating sections for maintenance. Metering and sampling are routine tasks at intake points. Flow meters provide continuous records of the volume entering treatment. Grab samples or automated samplers collect raw water for laboratory analysis. Parameters commonly tested include turbidity, pH, temperature, and basic indicators of organic content. These data support decisions about coagulation, sedimentation, and filtration steps later in the treatment train. Intake systems are the first engineered interface between a natural water source and a treatment facility. Their design and operation set initial conditions for subsequent processes. Control of flow, removal of large solids, and protection of mechanical equipment are primary functions. Attention to placement, screening, and monitoring allows a treatment facility to receive source water reliably and with predictable characteristics. Water entering a treatment facility first passes through physical systems designed to remove large and heavy material. These systems act before chemical or biological processes. They reduce abrasion, blockages, and sediment accumulation. They rely on mechanical separation and controlled flow paths. The processes are steady and predictable. The emphasis is on removing particles by size and weight. Mechanical screening is usually the initial step. A screen is a barrier with openings sized to retain large objects while allowing water to pass. Coarse screens have wide openings. They stop branches, rags, and large debris. Fine screens have narrower openings. They capture smaller solids and some organic matter. Screens are mounted at intake channels or in enclosed housings. Water approaches the screen at a controlled speed. The approach velocity affects what is captured. Slower approach speeds allow more solids to be retained. Faster speeds may push material through or cause clogging. Screens come in several forms. Bar racks are simple and robust. Bars are spaced at regular intervals. Inclined racks use gravity to move captured debris upward along the bars. Chain and rake systems employ a mechanical rake that travels along guide rails. The rake lifts material from the screen and deposits it into a collection hopper. Perforated plate screens and woven wire screens provide finer separation. Rotating drum screens allow continuous screening. The drum rotates while water flows through its perforated surface. Solids accumulate on the outside and are carried to a disposal conveyor or wash trough. Screens may include compactors or crushers to reduce the volume of captured material. After coarse screening, grit removal follows. Grit consists of small, dense particles such as sand, gravel, and silt. These particles settle more rapidly than organic solids. If left in the system, grit will abrade pumps and settle in pipes and tanks. Grit removal focuses on separating dense inorganic particles without capturing light organic matter. This keeps later biological processes more efficient. Several mechanical approaches address grit removal. Gravity settling basins slow the water to a velocity at which grit falls to the bottom, while lighter material remains suspended. The basins are shaped to promote sedimentation along a predictable path. Vortex grit chambers create a circular flow. The centrifugal motion moves heavier particles to the bottom center where they collect. Aerated grit chambers introduce small bubbles to maintain lighter particles in suspension while heavier particles settle. The bubbles also help to lift settled material toward removal mechanisms when needed. Hydrocyclones use centrifugal force in a conical chamber to separate particles by density. Flow enters tangentially and spins. Heavier particles move to the outer wall and descend for collection. Each method separates grit with minimal loss of organic solids. Collected grit is removed by mechanical devices. Scrapers and hoppers gather settled material. Pumps or conveyors transport grit to classifiers. Grit washers remove organic content and reduce odors before disposal. The design minimizes water loss and prevents material re-entry into the channel. Grit is often stored temporarily before final handling or disposal. Proper handling reduces wear on downstream equipment. Sedimentation is the next broad category of mechanical separation. Sedimentation basins, also called primary clarifiers, give suspended solids time to settle by gravity. Flow enters gently to avoid resuspension. Baffles and inlet channels distribute flow evenly across the basin. Even distribution prevents short-circuiting, where water moves too quickly from inlet to outlet. Outlets are arranged as peripheral weirs that collect clarified water uniformly. The depth and residence time in a sedimentation basin influence the removal of settleable solids. Settled solids, known as primary sludge, collect at the basin bottom. Mechanical scrapers move along the basin floor. They gather sludge toward a central hopper or sump. From there, sludge is pumped or conveyed for further treatment, such as digestion or dewatering. Scum removal skimmers remove floating material from the surface. Skimmers travel slowly, collecting oils and light debris and directing them to a separate collection point. Clarifiers often include features to improve efficiency. Lamellar plates increase the effective settling area within a smaller footprint. The plates are inclined and closely spaced to create multiple short settling paths. This arrangement allows finer particles to settle more readily than in a traditional open basin. Tube settlers perform a similar function. Both systems reduce the space required while maintaining effective sedimentation. Flow regulation underpins mechanical separation. Separation efficiency depends on stable hydraulic conditions. Sudden surges or drops in flow alter settling behavior. Flow regulators aim to maintain a steady rate through screens, grit chambers, and clarifiers. Equalization basins provide temporary storage during peak flows. Water is held and released at a controlled rate downstream. This evens out variations and protects biological processes from hydraulic shock. Mechanical gates, sluices, and orifices control water levels and velocities. These devices are sized to produce specific flow profiles. Automatic actuators adjust gate positions in response to level sensors. Variable speed pumps also play a role. By changing pump speed, the system can modulate flow without altering upstream conditions abruptly. Flow meters monitor the volume of water passing through channels. Data from meters inform control logic that governs valves and pumps. The control systems aim for gradual changes rather than abrupt shifts. Hydraulic design reduces turbulence where sedimentation is required. Inlets use dissipators and baffles to slow and distribute water. Outlet structures capture clear water gently. Energy dissipation prevents resuspension of settled particles. Designs include weir skimmers with adjustable vanes to maintain uniform collection along the entire perimeter of a basin. Maintenance is part of continuous operation. Screens require inspection and cleaning. Mechanical rakes are checked for wear and alignment. Grit chambers need periodic removal of accumulated material. Sedimentation basins undergo desludging to maintain storage capacity and settling performance. Scheduled maintenance keeps hydraulic conditions within designed parameters. Monitoring complements mechanical measures. Visual inspection, level sensing, and particle load measurements provide feedback. Operators use these observations to adjust flow, controls, and scheduling. When solids load increases, screens and grit removal may require more frequent cleaning. When flows dip, equalization systems release stored water to maintain steady downstream conditions. The goal is consistent separation performance. Mechanical separation and flow regulation form a coordinated sequence. Screens remove large solids. Grit removal targets dense inorganic particles. Sedimentation clarifies water by allowing suspended material to settle. Flow regulation ensures that each step operates under conditions conducive to separation. Together, these systems protect downstream processes. They reduce wear on equipment and improve the efficiency of chemical and biological treatment stages that follow. Fine particles in water are removed by passing the flow through filtration systems composed of layers of material. Filtration is a physical process. It relies on removal by interception, straining, and adhesion as water moves through media. The design of a filtration system determines how particles are captured and how the water moves after capture. A common approach is granular media filtration. Granular filters use layers of particulate media arranged by size and density. Typical media include sand, anthracite coal, and heavier fine gravels or garnets. Each layer has a defined particle size range. Larger, lighter media sit above smaller, denser media. Water flows through these layers. As it does, larger particles are trapped near the top. Finer particles are carried deeper and captured in the lower layers. The arrangement spreads the solids through the depth of the bed, rather than confining them to the surface. This process is called depth filtration. Multimedia filters are a variant of granular media filters. They use at least two different materials in distinct layers. A common configuration places anthracite at the top, a layer of sand below it, and a layer of finer sand or garnet at the bottom. Anthracite particles are relatively large and have lower density. Sand particles are smaller and denser. Garnet or other heavy media at the base provide fine support and prevent media loss to the underdrain. The graded arrangement creates a larger effective filtration area. It also delays clogging onset because particles accumulate in several layers. The movement of particles into progressively finer layers is steady and predictable. Slow sand filtration uses a single, fine sand layer in a deep bed. Water moves slowly through the sand. Over time, a biological and particulate layer forms on the sand surface. This layer contributes to particle removal and some biological activity. The slow filtration rate keeps the surface layer intact while allowing clarified water to pass downward. Periodic maintenance requires scraping the top sand layer and replacing it. The principle of slow sand filtration is simple. Small pore spaces and prolonged contact time produce effective removal of fine particles and some associated contaminants. Activated carbon is often used as a separate media layer or in its own dedicated bed. Granular activated carbon acts by adsorption. Organic molecules and certain dissolved substances adhere to the carbon surface. In the context of particle removal, carbon beds can trap particulate matter and adsorb dissolved organic material that may contribute to taste or odor. Carbon has a high internal pore surface area. Over time, the adsorption sites fill. Regeneration or replacement of carbon is necessary to maintain performance. Powdered activated carbon can be added upstream of a filter and removed with the particulates during filtration. Membrane processes present a contrasting approach. Microfiltration and ultrafiltration rely on physical pore sizes to separate particles from water. Microfiltration membranes have larger pores and remove suspended solids and some bacteria. Ultrafiltration membranes have smaller pores and can retain finer colloids and many viruses. Membranes are arranged in modules. Common geometries include hollow fiber, spiral wound, and flat sheet. Water is forced through membrane surfaces under pressure. Particles larger than the pore size remain on the feed side and are removed by periodic cleaning. Membrane fouling is managed by backwashing, air scouring, and chemical cleaning. The operation is continuous in many systems, with timed cleaning cycles to restore permeability. Under-drain systems support the media layers and collect filtered water. Under-drains may include perforated plates, collector laterals, or modular distributor systems. A transition layer of gravel or coarse media often rests above the under-drain. The gravel provides uniform support and prevents finer media from migrating into the collection system. Head loss develops across a filter bed as particles accumulate. Monitoring head loss helps determine when a cleaning cycle is required. A controlled increase in head loss is expected during normal operation. Backwashing is the routine cleaning procedure for granular media filters. During backwash, flow is reversed and often combined with air scouring. Water or water with air flows upward through the bed. The reversed flow expands the media, dislodges accumulated particles, and carries them to a waste channel. Backwash rates and durations are selected to fluidize the bed enough to release trapped solids without scouring media itself. The removed solids form a suspension in the backwash water. That suspension is collected and treated or disposed according to regulatory and operational practice. Backwashing restores the hydraulic performance of the bed and resets head loss. Surface wash systems provide supplemental cleaning. They direct water jets across the top of the bed to remove material concentrated at the surface. Surface wash is useful after sedimentation processes that pass larger flocks to the filter. When the top layer traps a disproportionate amount of solids, a short surface wash can extend the time between full bed backwashes. Surface wash systems operate at the beginning of a cleaning sequence. They reduce the volume of backwash water needed for full cleaning. Filtration performance depends on several controllable parameters. Filter loading rate, often expressed as flow per unit surface area, affects contact time and capture efficiency. Slower loading allows greater opportunity for particles to be retained. Media, effective size and uniformity coefficient influence pore structure and straining characteristics. Media density affects settling during backwash and layer stability. Bed depth determines how many particles can be collected before cleaning. Designers select these parameters to meet water quality objectives and operational constraints. Filtration is closely linked to upstream clarification. Coagulation and flocculation increase particle size and encourage settling. Sedimentation or clarification removes a portion of solids before the filter. The remaining fine particles and any dissolved substances pass to the filter for additional removal. When pre-treatment is effective, filters operate with lower solids loads and require less frequent backwashing. When pre-treatment is less effective, the filter must handle more solids and cleaning intervals shorten. Instrumentation and control support steady operation. Flow meters, turbidity sensors, and differential pressure gauges provide continuous information. Turbidity in filtered water indicates remaining particulate content. Differential pressure across the bed indicates head loss. Operators use these readings to schedule backwash cycles. Automated control systems can initiate cleaning based on set points. Manual intervention remains part of many systems for adjustments and inspections. Material selection also considers chemical compatibility and physical durability. Media exposed to oxidants or corrosive substances must resist degradation. Abrasion resistance matters under frequent fluidization during backwash. Density differences between media types must be sufficient to maintain layer separation during operation and cleaning. When multiple media types are used, their interaction during backwash is an important design consideration. Finally, filtration systems are monitored for performance and integrity. Routine sampling and laboratory analysis verify that particle removal meets specifications. Visual inspection of media condition, under-drain function and backwash clarity complements instrumentation data. When media performance declines permanently, media replacement or media reclassification may be scheduled. The goal of these practices is consistent removal of fine particles while maintaining steady hydraulic performance. Filtration therefore combines mechanical, physical, and in some cases, chemical processes. Layered media create a controlled path for water. As the water moves, particles are intercepted, strained, or adsorbed. Periodic cleaning restores the media. Monitoring maintains operational balance. These elements together form the practical and repetitive work of removing fine particles in continuous water treatment applications. Chemical treatment and disinfection are routine activities within a continuous water treatment system. The objective is to alter water properties in predictable ways, to remove particles and organic matter, and to reduce microbial concentrations to defined levels. Treatments are applied in measured amounts. The process emphasizes consistency and controlled dosing more than the detailed chemistry of reactions. Coagulation and flocculation are common chemical steps. Coagulants, typically metal salts such as aluminum or iron compounds, are added in low concentrations. These chemicals destabilize fine suspended particles. Polymers are often used as flocculants. They encourage particles to join into larger aggregates. Mixing energy and retention time are controlled to allow particles to form flocks. Settling or filtration equipment then removes those aggregates. Dosing systems are adjusted according to raw water clarity and turbidity. When turbidity rises, dosing is increased in a controlled manner. When turbidity declines, dosing is reduced. The goal is steady performance rather than abrupt changes. pH adjustment is another routine measure. Some treatment steps work better at specific pH ranges. Alkalis or acids are added to move pH toward a target value. Common reagents include lime, sodium hydroxide, or acidic solutions when reduction is needed. pH control is typically automated. Sensors report pH continuously. Controllers adjust dosing to maintain the set point. Slow changes are preferable. Rapid swings in pH can reduce the effectiveness of subsequent treatment steps or stress equipment. Therefore, adjustments are incremental and monitored. Disinfection is a distinct stage with a separate set of controls. The primary aim is to maintain a measurable disinfectant concentration through the distribution system. Several disinfectants are commonly used. Free chlorine, applied as gas or as sodium hypochlorite solution, remains the most widely used. Chloramines are formed by combining ammonia with chlorine and are used to provide a longer-lasting residual in distribution networks. Ozone is applied in some plants for strong, short-term oxidant effect, typically before filtration. Ultraviolet light provides non-chemical disinfection by inactivating microorganisms as water passes through reactors. Each disinfectant requires a specific approach to dosing and monitoring. Controlled dosing relies on metering pumps and feed systems that deliver chemicals at set rates. Pumps may be proportional to flow, where the dose rate varies with the measured flow of water. Alternatively, dosing may respond to online water quality measurements, such as residual disinfectant, turbidity, or pH. Modern systems often combine both approaches. Flow proportional dosing provides a baseline that matches water volume. Feedback from analyzers fine-tunes dosing to maintain target concentrations. Online analyzers play a central role in consistency. Instruments measure parameters such as free chlorine, combined chlorine, pH, turbidity, and oxidation reduction potential. These readings are logged and compared to set points. Control systems use the data to adjust feed rates. Trending is common practice. Operators observe trends to anticipate changes rather than reacting to sudden deviations. Continuous monitoring reduces the need for large manual interventions. Residual management is a practical focus in disinfection. A measurable residual is the concentration of disinfectant remaining after contact time in treatment and distribution. Maintaining a target residual helps ensure that disinfection objectives are met beyond the plant. Residual values are selected to balance microbial control with byproduct formation and water quality considerations. The selection of a target residual involves operational constraints and regulatory expectations. Once set, the target is maintained by coordinated dosing and monitoring. Contact time is accounted for in design and operation. Contact time is the duration water spends in a contactor or reservoir where disinfectant and water mix. Contactors are sized and configured to provide predictable contact time at normal flow rates. Because flow varies, contact time calculations often use conservative values and consider hydraulics to avoid short-circuiting. Dosing points are located to maximize effective contact while maintaining process control. Disinfection byproduct management is part of operational planning. Chlorine reacts with natural organic matter to form byproducts such as trihalomethanes and haloacetic acids. Operators manage precursor levels upstream through coagulation and filtration, and they adjust disinfectant strategies to reduce byproduct formation. Options include altering dose timing, using chloramines, or applying alternative disinfectants for part of the treatment train. Monitoring for byproducts is performed according to regulatory schedules. Decisions about dosing strategies consider both disinfection performance and byproduct trends. Calibration and maintenance of instrumentation are routine tasks. Sensors drift over time and require regular calibration against standards. Metering pumps need inspection and occasional replacement of diaphragms, seals, and tubing. Chemical feed lines are checked for leaks and blockages. Scheduled maintenance reduces variability in dosing. Records of calibration and maintenance are kept to document performance and support adjustments. Redundancy and backup systems contribute to continuous operation. Critical components, such as dosing pumps and analyzers, are often installed in pairs. A secondary pump can take over if the primary unit fails. Electrical backup systems maintain power to feed systems during interruptions. Alarms alert staff to deviations in measured parameters. Response procedures define steps for adjusting doses, switching equipment, or taking samples when alarms occur. These procedures are standardized and aim to restore controlled conditions promptly. Chemical storage and handling follow defined procedures. Chemicals are stored in designated tanks or containers with containment measures to limit releases. Transfer and feed lines have valves and monitoring to control flow. Mechanical mixers in chemical storage tanks keep concentrated solutions homogeneous. Delivery schedules and inventory management ensure that required reagents are available to maintain consistent dosing without interruption. laboratory support complements online monitoring. Grab samples are collected regularly and analyzed for parameters that may not be measured continuously, such as microbial indicators, certain byproducts, or total organic carbon. Results from laboratory analyses inform adjustments to chemical dosing and process configuration. Comparison between online analyzers and laboratory results ensures accuracy and supports calibration schedules. Data logging and supervisory control systems integrate dosing, monitoring, and historical records. Control rooms display trends and alarms. Set points are adjusted through human-reviewed procedures. Records provide a basis for audits, reporting, and optimization studies. Continuous data allows for gradual process improvements aimed at maintaining consistent treatment performance over long periods. Overall, chemical treatment and disinfection within continuous systems are governed by measurement, control, and routine intervention. The emphasis is on predictable dosing, consistent monitoring, and documented procedures. Adjustments are incremental and based on measured conditions. The operational objective is steady performance achieved through controlled inputs and continuous observation. Monitoring systems measure water quality, pressure, and flow continuously across a treatment facility. Their role is to provide data that describes current conditions. That data informs automated controls and human decision-making. It is collected at multiple points. It is transmitted, logged, and displayed in a control environment. Water quality measurement covers a range of physical and chemical parameters. Turbidity sensors detect cloudiness caused by suspended particles. pH probes monitor acidity and alkalinity. Conductivity probes measure the ability of water to carry electrical current, which relates to dissolved ions. Residual disinfectant analyzers measure the concentration of chlorine or chloramine remaining after disinfection. Temperature sensors record water temperature. Dissolved oxygen probes measure oxygen content in specific processes, such as aeration basins. Some facilities include online analyzers for nitrate, ammonia, or total organic carbon. These instruments operate continuously or at set intervals and provide near real-time readings. Flow measurement devices report the volume of water moving through pipes, channels, and conduits. Magnetic flow meters are common in metal or lined pipes. Ultrasonic flow meters measure flow without inserting parts into the fluid in some applications. Differential pressure devices, like Venturi meters and orifice plates, infer flow from pressure differences. Turbine meters use a rotating element to count volume. Flow sensors are installed at intakes, between treatment units, and on distribution mains. They allow operators to track rates of intake, treatment, and delivery. Pressure monitoring uses transducers and gauges. Pressure transducers convert fluid pressure into an electrical signal. They are placed at pump outlets, at key junctions in the piping network, and at distribution zone boundaries. Pressure readings show pump performance and pipeline conditions. Sudden changes in pressure can indicate leaks, blockages, or changes in demand. Pressure data supports pump control and helps maintain target pressures in the network. Level sensors track liquid heights in tanks, basins, and reservoirs. Ultrasonic level sensors emit sound pulses and measure return time. Submersible pressure transmitters infer level from hydrostatic pressure. Float switches provide a simple mechanical indication of high or low levels. Level data is used to manage tank fill, to sequence pumps, and to prevent overflow or emptying. Sensors output signals in a few standard formats. Analog currents, commonly 4 to 20 milliamps, are widely used. Digital communication protocols such as Modbus or HART provide richer data and diagnostics. Signals feed into programmable logic controllers or PLCs, which execute control logic. The PLCs in turn connect to supervisory control and data acquisition systems, called SCADA. SCADA systems aggregate data, log historical records, and present dashboards for monitoring. They also record alarms and events. Signal integrity and data quality are important. Sensors require calibration at intervals to maintain accuracy. Calibration may use reference solutions or field standards. Some instruments include automatic zero and span checks. Routine cleaning prevents fouling from biofilms or particulates. Maintenance schedules document calibration dates, adjustments, and replacements. Logs of maintenance support traceability and regulatory compliance. Sampling complements online monitoring. Grab samples are taken for laboratory analysis when online instruments cannot measure a parameter reliably. Laboratory tests include biochemical oxygen demand, total suspended solids, and certain organic or microbial analyses. Results from the lab validate online measurements and provide additional data for regulatory reporting. Sampling locations are chosen to represent specific process stages or points in the distribution system. Alarms and set points are configured to respond to parameter deviations. Thresholds mark when a reading requires attention. Alarms are routed to control room consoles and to remote operators through paging or electronic messages. Some alarms trigger automatic responses. For example, a high turbidity alarm may initiate a backwash cycle on a filter. Control loops use proportional integral derivative logic to adjust valves and pumps based on sensor inputs. These loops maintain targets for flow, pressure, and certain water quality parameters. Redundancy reduces the risk of undetected instrument failure. Critical points often have 2 or more sensors of the same type. Comparative readings reveal sensor drift or malfunction. Voting logic can allow a system to ignore a single outlier reading. Backup power supplies and redundant communication paths help maintain monitoring during power or network disturbances. Data management includes storage, review, and reporting. Time-stamped data records enable trend analysis. Operators review trends to detect slow changes that may not trigger immediate alarms. Trend analysis aids in optimizing chemical dosing, pump scheduling, and energy use. Historical data also supports regulatory reporting requirements. Records demonstrate compliance with discharge permits and water quality standards. Integration with maintenance systems improves reliability. When a sensor reports out-of-range values or diagnostic faults, the monitoring system can generate a work order. Maintenance personnel receive details about the affected instrument and its location. That process shortens response times and keeps instruments functioning within specifications. Security measures protect data and control connectivity. Network segmentation, user authentication, and encryption are common practices. Access controls limit who can change set points or override automatic responses. Audit logs record configuration changes and operator actions. These measures preserve data integrity and maintain consistent operation. Remote monitoring extends visibility beyond the control room. Telemetry units transmit data from remote sites using wired networks, cellular links, or radio. Remote stations commonly report flow and level at intakes, pump station status, and reservoir levels. Remote data supports centralized decision-making and scheduled field maintenance. Validation and quality assurance programs ensure that monitoring data is reliable for operational and regulatory use. These programs specify calibration intervals, acceptable measurement uncertainty, and procedures for handling out-of-range values. Control charts and statistical checks identify trends in instrument performance. Corrective actions follow documented procedures when instruments fall outside acceptable limits. In summary, monitoring systems in water treatment facilities combine sensors, signal processing, control logic, and data management. They measure key variables such as turbidity, pH, conductivity, residual disinfectant, flow, pressure, and level. Data from multiple, often redundant sensors feeds control systems and supervisory software. Calibration, maintenance, sampling, and data validation keep measurements reliable. The resulting information supports continuous operation, regulatory compliance, and efficient process control. After treatment, water enters a controlled storage system that sits between the plant and the distribution network. Storage provides a steady source of water to meet varying daily demand. It also serves as a buffer for short-term changes in consumption and for changes in supply. Storage and pressure management together determine how water moves from treatment facilities into homes, businesses, and public services. Storage takes several forms. Clear wells and holding basins at treatment sites provide immediate short-term storage. Ground-level reservoirs and covered tanks offer larger volume storage near the plant. Elevated tanks and towers store water at height to provide sustained pressure without continuous pumping. Underground reservoirs and covered ground tanks are used in locations where elevation or space constraints make elevated storage impractical. Each type of storage performs similar functions, but they do so through different physical arrangements. One fundamental purpose of storage is to maintain a consistent water supply during cycles of demand. Daily demand typically follows predictable patterns. Morning and evening peaks often require more water than midday or overnight periods. Storage systems hold water during low demand. They release it steadily during peak use. This reduces the need for continuous high-capacity pumping and allows pumps to operate more efficiently on a scheduled basis. Pressure management is closely linked to storage. Pressure in a water system is created by either height or mechanical means. Elevated tanks create pressure by the height of the water column. Pumps create pressure by adding energy to the water. In many systems, a mix of elevation and pumping provides a stable range of pressures across the network. Pressure must be controlled to prevent excessive stresses on pipes and to ensure adequate flow at consumer connections. Zones are a common method of managing pressure. A service area may be divided into pressure zones. Each zone has storage and pressure control equipment sized for its elevation and demand. Pressure-reducing valves regulate flow into lower zones when fed from higher pressure sources. Conversely, booster pumps or pump stations add pressure for higher zones. This arrangement keeps pressure within target ranges for each area, while allowing the distribution grid to operate smoothly. Automation and monitoring play a key role in controlling storage and pressure. Level sensors monitor water levels in tanks and basins. Flow meters measure the rate of water leaving treatment facilities. Pressure transducers monitor pressures at critical points in the network. These instruments feed data into supervisory control systems. The control systems start and stop pumps, open and close valves, and adjust pump speeds. Automation reduces manual intervention and enables more precise response to changing conditions. Variable speed drives are commonly used on pumps to adjust flow and pressure smoothly. A variable speed drive alters pump rotation speed in response to a control signal. When demand increases, the drive raises pump speed to maintain set points. When demand decreases, the drive lowers speed to avoid overpressurizing the network. This results in less mechanical cycling and more efficient energy use than simple on-off pump control. Surge and transient conditions require specific management. Sudden changes in flow can produce pressure surges or drops. Surge tanks, air chambers, and pressure relief valves mitigate rapid pressure changes. Surge tanks absorb excess pressure by temporarily storing a small volume of water. Pressure relief valves open to discharge water when pressures exceed safe thresholds, protecting equipment and piping. These elements act in fractions of a second to maintain steady conditions when flow patterns shift quickly. Turnover and mixing within storage facilities affect water quality. Water held for long periods can experience loss of disinfectant residual or stratification by temperature. Mixing systems and inlet-outlet designs promote circulation to reduce stagnation. Periodic flushing of distribution lines removes sediment and prevents water from sitting in dead ends for extended periods. Operational schedules are set to balance turnover with demand and to comply with water quality guidelines. Emergency and reserve storage are part of design criteria. Systems maintain a reserve to meet short interruptions in supply, planned maintenance, or unexpected high demand. Reserve volumes are sized based on service area needs, the reliability of supply sources, and regulatory guidance. Redundancy in pumps and power supplies supports continuous operation during component outages. Backup generators and multiple pump units provide layers of redundancy that keep water moving until normal conditions are restored. Coordination between storage and pumping is important for daily efficiency. Pump schedules are often based on forecasted demand and on real-time measurements. During low-demand periods, pumps refill storage. During high-demand periods, pumps supplement the flow drawn from storage. Optimization strategies aim for minimal cycling of equipment and for maintaining target pressures with the least energy use. Predictive algorithms and historical demand profiles assist in planning pump operation. Hydraulic losses in the distribution network affect pressure at endpoints. Friction losses in pipes, fittings, and valves reduce available pressure as water travels. Pipe diameter, material, age, and flow velocity all influence these losses. Pressure management accounts for these factors through design and through active control. Monitoring pressure at multiple points helps identify areas with high losses or with the need for infrastructure upgrades. Valves and flow control devices shape how water is released from storage. Float valves, motor-operated gates, and automated control valves regulate levels and flows. Weirs and overflow structures set limits and protect against uncontrolled spills. Check valves prevent reverse flow. The operation of these devices is coordinated by the control system to maintain stability across reservoirs and tanks. Documentation and routine inspection support reliable storage and pressure management. Operators review instrumentation readings, log events, and perform scheduled maintenance. Sensors are calibrated, valves are exercised, and tank interiors are inspected when necessary. These practices maintain functional performance and detect issues before they propagate through the system. Overall, storage acts as a buffer between production and use. Pressure management ensures water moves at an appropriate rate and reaches service connections with sufficient force. Together, these systems provide a steady release of water that responds to both predictable patterns and unexpected variation. The design and operation of storage and pressure systems balance hydraulic principles, equipment capabilities, and operational constraints to maintain continuous service. Long-term operation of water treatment systems depends on regular maintenance and built-in redundancy. Both elements work together to allow treatment to continue without interruption. Maintenance keeps equipment functioning within expected limits. Redundancy provides alternative capacity when parts of the system are taken out of service for inspection, repair, or replacement. Maintenance is scheduled at multiple intervals. Some tasks occur daily, others occur weekly, monthly, or annually. There are also tasks on longer cycles, measured in years. Daily tasks include visual inspections of pumps, valves, and instrumentation. Operators check pump pressures, flow rates, and basic alarms. Chemical storage levels are checked. Turbidity and chlorine residuals are monitored through routine sampling. These frequent checks identify trends. Small deviations can be corrected before they affect overall operation. Weekly and monthly tasks are more detailed. Pumps and motors receive lubrication according to manufacturer guidance. Filters are monitored for head loss and scheduled for backwash when necessary. Backwash cycles are often automatic, but they are reviewed to confirm they proceed as intended. Valves are exercised on a planned basis to prevent sticking. Chemical feed systems are inspected for dosing accuracy. Instrument sensors are cleaned and examined for drift. These tasks preserve performance and reduce the likelihood of sudden failures. Annual and multi-year tasks focus on components with longer wear cycles. Filter media may be renewed after several years of service. Membrane elements in membrane filtration systems undergo cleaning and, when required, replacement on a planned interval. Corrosion inspections and coatings are addressed on a multi-year timetable. Mechanical seals and bearings are replaced according to life estimates or condition-based indicators. Electrical switchgear and backup power systems are tested on annual cycles. These longer-term interventions sustain the system's life cycle. Predictive maintenance adds a different dimension. Condition-based monitoring uses data to anticipate failure before it occurs. Vibration analysis of rotating equipment can indicate bearing wear. Thermography can reveal loose electrical connections. Trends in pump energy consumption can point to impeller erosion. Regular analysis of these indicators informs targeted interventions. Predictive actions extend component life and limit unscheduled outages. Documentation supports all maintenance work. Work orders, asset registers, and maintenance histories are kept current. Each piece of equipment has a record of inspections, repairs, and parts replaced. Manufacturers' manuals and calibration certificates are maintained. Clear records allow planners to identify recurring issues and to plan replacements at appropriate intervals. A documented spare parts inventory is matched to these records. Critical spares are identified and held in stock to shorten repair times. Redundancy is a deliberate design principle. It provides spare capacity and alternate pathways. common approach is an N+1 configuration. In this model, one additional unit exists beyond the number required to meet normal demand. Pumps, filters, and chemical dosing trains are often arranged in parallel. If one unit requires shutdown, the parallel units carry the load. This permits maintenance without loss of treatment capability. Physical redundancy includes parallel process trains and bypass lines. Parallel trains allow flow to be shifted from one set of tanks to another. Bypass lines provide a route around a specific unit. By closing and opening valves, flow is rerouted while work proceeds. Distribution reservoirs and storage tanks add temporal redundancy. They can supply treated water for a limited time while parts of the treatment process are offline for maintenance. This buffer helps prevent interruptions in service to the downstream network. Redundancy extends to power and control systems. Backup generators and uninterruptible power supplies provide electrical redundancy for essential equipment. Control systems may include duplicated servers, redundant network paths, and failover configurations. Supervisory control and data acquisition systems record operational data and alert operators to abnormal conditions. Redundant instrumentation helps validate measurements. Two independent sensors on the same point can reduce the chance of erroneous readings leading to incorrect actions. Operational protocols govern how redundancy is used. Planned outages are scheduled during periods of lower demand when possible. Staged switching sequences move flow gradually from one train to another. Acceptance tests confirm that a train returns to service as designed. These procedures reduce transient disturbances. They also protect equipment from unintended stress caused by abrupt changes in flow or pressure. Temporary measures support continuous operation when long repairs are required. Mobile treatment units can be deployed to provide capacity while permanent components are serviced or replaced. Portable pumps and temporary piping systems are used for short-term rerouting. Contracts with vendors and mutual aid agreements with nearby utilities provide access to specialized equipment and personnel. These arrangements are part of contingency planning for extended maintenance needs. Maintenance planning includes life cycle considerations. Engineers estimate the useful life of major components and incorporate replacement into long-term budgets. Capital renewal plans schedule phased replacements to spread cost and to maintain capacity. Condition assessments feed into these decisions. When components approach the end of their useful life, planned replacement is preferred over reactive repair. Planned replacement is generally faster and more predictable than emergency work. Training supports long-term operation. Operators and maintenance staff are trained on procedures, equipment handling, and repair techniques. Training programs include updates when new technologies are introduced. Cross-training ensures that multiple staff members can perform essential tasks. This reduces dependence on a single individual for specialized repairs. It also supports continuity when staffing. Changes occur. Testing programs verify system readiness. Regular start-stop tests of standby equipment confirm operational readiness. Simulated failover tests validate redundancy in control systems. Water quality testing continues during and after maintenance actions to confirm that treatment objectives are met. Calibration checks on analytical instruments ensure that test results remain reliable. Test records become part of the operational documentation. Procurement and supplier relationships influence long-term reliability. Standardization of components reduces the variety of spare parts required. Long-term service agreements with manufacturers provide timely access to replacement parts and technical support. Inventory management balances holding costs against the risk of prolonged downtime. Decisions on what to stock are informed by component criticality and lead times for procurement. Regulatory compliance shapes maintenance cycles as well. Inspection intervals and testing requirements are often specified in regulations or permits. Compliance schedules drive certain activities, such as annual sanitary surveys or periodic discharge monitoring. Meeting these obligations aligns with the operational need to maintain continuous treatment. Over time, incremental improvements are incorporated. System upgrades may introduce more efficient pumps, longer life membranes, or improved control algorithms. These upgrades are planned to integrate with maintenance cycles. Gradual modernization preserves capacity while reducing long-term operating costs. The combination of scheduled maintenance, predictive monitoring, documented procedures, and system redundancy forms the foundation for continuous treatment operation. Each element contributes to the avoidance of unplanned interruptions. Together, they create a framework in which routine care and deliberate backup capacity sustain water treatment systems through years of service.